Welcome to Music 320 Week 8. And this week we're going to be covering concepts such as additive synthesis, modulation, that would be frequency modulation, amplitude modulation, ring modulation, and then we'll be looking at the poly and polytilde objects. So we're going to start with just a relatively quick video dealing with the concept of additive synthesis. So additive synthesis is based on Fourier's theorem, and Fourier was a psychoacoustician or an acoustician who came up with the theory that all complex sounds could be expressed as the sum of their component sine waves. And essentially what Fourier is saying is that if we want to create a particular complex sound, all we have to do is know what the harmonic components are of that sound, what frequencies are contained within that sound, and we need to know what the the amplitude envelopes of each of those frequencies is. And if we can put together all the component frequencies of a sound with the right envelopes, then we can recreate that sound. And what essentially happens is that we know that a complex timbre, such as, let's say, a clarinet tone, consists not of just one frequency, but a frequency and a whole series of overtones, and that all those overtones have different envelopes, amplitude envelopes on them. They don't all follow exactly the same envelope as the fundamental does. So that's the concept of additive synthesis. We can create a complex sound by simply adding together sine waves, or other waves if we choose to do so, at different frequencies. And those sounds, or those frequencies that we use to add together to create a complex sound, can either be harmonic frequencies or harmonic partials, or they can be inharmonic frequencies or inharmonic partials. Harmonic partials are going to be integer multiples of the fundamental frequency, and inharmonic partials are going to be non-integer multiples of the fundamental frequency. Okay, so in this particular example, let me just put my sound on and give myself some volume. I just have a bang button here that's going to trigger 3 different bangs, and I have 3 different envelopes. The second outlet of each of these envelopes goes into a line object, and this line object is used to do an amplitude controls on 3 different frequencies, 3 different sine waves. One of them is at 400, one of them is at 800, and one of them is at 1200. So these are harmonic partials because 800 is an integer multiple of 400, as is 1200. So this would be the fundamental, the second partial, and the third partial, and they're harmonic. What I've done in here, I've sort of played around with these envelopes a little bit, and I've made it so that the first fundamental, the first partial, has more of its higher amplitudes at the beginning of the sound. The second one has higher amplitudes in the middle of the sound, and the third partial has higher amplitudes towards the end of the sound. Okay? And let's see. And I'm going to bang this, and they're all going to mix together and not create 3 perceived frequencies, but they're going to create what most people will perceive as one pitch with harmonics or with partials. So I'll do that. Okay, and there you hear. So that little color change that you hear in the sound, I'll put the domain of the envelopes all at 5,000. So you can hear the sound brightening up at the end, and that's because the fundamental is strongest at first, and the third partial is strongest near the end of the sound. And so you get that sort of sense of dynamic change in the sound. If I change these to, I'm going to make this 1200 and this 2000, these are still harmonic partials, But if this is the first, this is the fundamental or the first partial, this would be the third partial, and this would be the fifth partial. And that combination of partials will give us something that sounds a little bit more like a clarinet. Right? Put the fundamental down. Okay. So different combinations of partials will give us different colors. And of course, if we use inharmonic partials, such as 636 and 721, those are just arbitrary numbers, we get something that sounds like this. Now, because they're inharmonic partials, it starts to become easier to sort of separate the individual frequencies from the sound. So some people will hear that as being three frequencies, three different sounds coming on top of each other, and some people will just hear it as a color, as a single timbre. Well, basically one frequency with a complex timbre. Okay, and let's go back to what we had with 800 and 1200. Okay, now I want to look at the panning down below here. I've got a patcher called do pan, and I've got a panning control which goes into the do pan. And I'm going to open that up so you can have a look at what's going on in here. Okay, panning. It turns out that panning, if you have a single audio source and you want to split it between two speakers, it does turn out that if you put all of the amplitude on one speaker and none in the other, or all of the amplitude in the other speaker and none in the other, and mix some proportion of the two signals, the sound will appear to be located somewhere between those speakers. So logic would tell us that if we want to put the sound a quarter of the way, we want it to be perceived as being quarter of the way between this speaker and 3/4 of the way from this speaker, that we would use a value of 0.25 and 0.75. And if we want it to be centered, we use a value of multiply one side by 0.5 and one other side by 0.5, and the sound will appear in the middle. And that is basically the principle we use for doing panning. We take a signal and we split it proportionally between two sources. And the more amplitude we put in on one side, the closer the sound will appear to being on that side. But there's a little bit of a quirk, or something that doesn't quite work perfectly well. And that's, you'll see this note in here, which says the intensity of a sound, that's the perception of the loudness of a sound, is equal to the square of its amplitude. So using a linear division of sound and splitting it linearly doesn't work perfectly well. What will happen is the sound will seem, overall, it will seem quieter when it is split between the two speakers as it will if it's all in one speaker or all in the other speaker. So in order to combat that, we use a square root object to basically deal with the fact that intensity, that perception of sound, is not the same as amplitude, which is the physical multiplication of sound. And so when we use a square root to multiply values, we're going to use between 0 and 1. When we take the square root of 0, we get 0. When we take the square root of 1, we get 1. When we take the square root of 0.5, we don't get 0.5. We actually get a larger number. We get 0.707. And so it turns out that as we move from right to left, using the square root of those two values, so rather than 0.25 and 0.75, we use the square root of 0.25 and the square root of 0.75, that when we do that, the perception of our sound moving smoothly in amplitude is created. So I'm just going to show you what happens here if I move 0. I take 0, this is between 0 and 100. I take 0, and that basically puts 1 on one side and 0 on the other, because the square root of 0 is 0 and the square root of 1 is 1. But if I go up, let's say, to 25, well, this becomes 0.25 and 0.75, but the square root of those values is not the same. The square root of 0.25 is actually 0.5, and the square root of 0.75 is 0.86. And if you add these two together, you see that it doesn't actually add up to 1. It's greater than 1, and that's what we want. So I'm going to put 50 in here, and this would be centered. And so rather than saying, well, the two amplitudes should be 0.5 and 0.5 if we want to split them equally, in fact, you'll get a better result if you use a value of 0.7 and 0.7, which of course all adds up to 1.4, not to 1. So, and similarly, if we go to 75, we'll get the reverse of what we had before. Okay? So essentially what's happening when we move from one side to the other is we use the square root of the division between 0 and 1 to give us the amplitude values that we need to make that transition smooth. Now I understand that's complicated. I just wanted to go over it. And for those of you who say, I don't want to know about this, then just ignore it. But in case you look inside and you see the square root object and you're wondering where in the world that came from, that is to compensate for the fact that amplitudes and our perception of intensity are not directly, they're not in line with one another. All right, so let's move my panning over to one side. I'll play a note. So I moved it there and back. And the sound should be moving from one speaker to another, and it should be perceived as overall being a smooth transition from one side to the other. Okay, I know that panning stuff was a little bit complicated. You probably didn't think you were going to have to deal with square roots, but it's in there. If, as I say, if you don't quite want to deal with it, then just ignore that. It's in there, and it works. Okay. That's all for week 8.1.